Okay. Now, this is something that I will have to clarify, but when you folks are done with the activity, are you able to go back and view it at a different time? Okay. Maybe someone, yeah, Richard, if you want to just try that over the break, because I think activities like this, I want to do more of those. Oh, if you make an account. Okay. Okay. So I think then maybe one of the things we can sort of put on the list of things to do this week is maybe create a Desmos account because, yeah, or maybe sign in with Google. I want you to be able to have access to these to go back and kind of play with them as we learn more content. I think it's important to come back and think about like the pictures that go with what we're doing because we're going to be doing a lot of algebra and stuff like that. But at the end of the day, we want to make sure that we know like what we're seeing, like what does a picture of what we're looking at actually look like, okay? Okay. And Natalia, you had signed in with your account? Okay. And Richard, you didn't, so then it didn't save. Okay, okay. So let me figure out how to add that to the list of things to do for this week. But I do want you to have access to go back and think about like what kind of stuff that you're using. Okay, so it sounds like if you just have a Google account, you could sign in with that. Then you can come back and play with these slides at your own pace. Okay. But what I'd like to do is this. I know that there was some confusion, which is to be expected, because I was like, here, play around with these different things, see what you think. But before we go on break, if we could do two quick things, okay? So this is back into your blank notes for today. What is the limit? So you've worked through some of this, if not all of this intro to limits activity on Desmos. And what I want us to do before we go on break real quick is, can someone share out maybe a concept that they learned from this activity? So let's start with the left-hand part. Are there any concepts that you feel like you learned during this activity? And you can either unmute yourself and say it out loud and I'll write it down, or you can type it into the chat, either or.
I would say that limits describe where the graphs exist.
Limits describe where the graph exists. Okay. Oof, gotta work on my teacher handwriting again.
I would say limits describe where the graph is going. So movement is integrated into the limit.
So limits describe where the graph is going. Is that what you said? Going. Uh-huh. Now Mean Girls finally makes sense. Mm-hmm. Describe where it approaches, where the graph is going, or where it approaches. Okay. And what do you mean by end behavior?
So like there's a point of discontinuity or maybe an asymptote. Like the graph technically ends there because it doesn't go past that, but like what does it do as it gets closer to the end of itself or that asymptote or a point of discontinuity?
Okay. All right, and all right, it's like zooming in on a really small part of the graph and describing what it does in just that section. So zooming in on a really small part of the graph and describe what's happening there. And then you know what happens on the left and the right of the point, or you have an idea, like maybe it's increasing or decreasing. Good, good. All of these are really good thoughts. Okay, now for questions. What kind of questions do we still have? And I think that's the tricky part, because sometimes we're like, I don't get it, but we sort of reached a stage in our learning where I don't get it is not enough to help us kind of move out of that stage, right? We need to be able to, by the end of this class, we really want to be able to form questions like, I don't understand this part, or how come here it does this, but over here it does that, okay? So are there any questions that are sort of lingering for people? Okay, so what about the last slide? That's a great example of how we can take something and like modify it so that it's a question. How can it not get close to a given x? What do you mean by that? Oh, like how can you have a limit that doesn't exist?
Yeah.
Okay. How can you have a limit that does not exist? I think that's a great question. All right, how can you have a limit that does not exist? Sketching, how does sketching work? You click on the, there's like a dot, so you can just draw, or there's like a pencil or a line, and then you can like draw a line on there. How do you sketch a picture based off on the limit? Is that what you mean? Okay. So how do we read limit notation? Also a great question. All right. And Richard, I missed this one earlier. Where does the limit not exist as x approaches a certain value? Okay, so kind of like how can you have a limit that doesn't exist? Okay, cool. Any other questions? So what is considered a limit? What can we do with them? Okay, cool. Well, think about this a little bit over our break, but I'm glad that we have some well-formed questions. I think that you'll find as we go through the next week and 2 weeks, that we'll be able to answer quite a few of these. So can we go backwards from a limit into a function? Like writing an equation that goes with the picture? I think I understand your question to be that, but yes, you can from a limit go backwards and sort of write an equation from where it came from, okay? Sometimes you can, and sometimes if you're just given the limit, there's actually multiple possible answers, okay? All right, so this seems like a good time to pause and take a break. Started. Okay, so let's see. You know, I've had so many first days of class, and I always think that I'm going to get through everything I'm going to get through, and I never do. And every year I'm like, why do I continue to think I'm going to get through all that I want to get through on that first day? But here we are. Okay, so right at the end of break, I dropped a link in the chat, and there should be one that says, hey folks, please join this class on Desmos. And so I see that 11 of you have already joined. I will post this link on Canvas as well, in case you need to create an account and that's just taking up too much time right now, you can do it later, okay? But I think let's give this a try, because I think I can assign activities through this. And then my hope is that you'll have a place where you can go back and look at all the different activities that we've covered, okay? So it'll be like a online binder for your Desmos activities for this class, okay? So let's try that out and see how it goes. But thank you folks for being so go with the flow. I really appreciate it. Oh, cool, nice. Yeah, if you have an account, then you can actually go back and see all the other stuff we've done as well. All right, so with that being said, let's go back to our notes and let's see how far we get today, okay? We're gonna end a little early. Like, I'd like to cut the lecture at 11:50 so we can just wrap up any loose ends, and there's a couple things that we need to talk about in terms of tutoring sessions, okay? So. All right. So before break, we were looking at some concepts from this activity, and we brought up some questions that we might have about limits, okay? Now, I know I heard from most people, but I also know that some of us haven't maybe typed some answers in the chat yet, which is fine. You don't have to contribute. But I do want to make sure that, you know, you're not just watching this and being like, wow, this is moving so fast, I have no idea what we're doing, okay? So even though I want to start doing more Desmos activities, that doesn't mean that we're not going to be doing lecture and doing practice and that kind of stuff, okay? But I do want us to kind of I want to encourage us to start to think about what we can actually figure out before we're formally introduced to a specific topic, okay? All right, so this notation. Okay, so this notation, that was actually one of the questions that folks had, which is how do we read this notation and like, what does it tell us, okay? So when we look at this particular question, here's what this says. So this sentence, if I were to read it, reads like this, okay? So the limit as x approaches a. Okay, so the limit as x approaches a of f of x is L. And so let's kind of color coordinate here, okay? So the limit, that LIM, is the part that reads limit, right? That part makes sense. But this little part, x arrow a, the way we read that is x approaches a, okay, of f of x, so of a given function that we're looking at, right? So sometimes we'll be given an equation for f of x, and sometimes it'll be a picture, but we'll know what we're looking at. And our answer to that question is going to be L. Okay, so that's just how we read it. So when we see that notation, as we did in like the what's new part of our notes, we would read that as the limit as x approaches a of f of x is L. But what does that actually mean? Okay, so if we wanted to unpack that even more, we might translate it for ourselves like this. The y value that the function gets really close to, okay? So the y value that the function gets really close to as x approaches a is the limit. Okay, so I'll give you a moment to write that down. But the y value that the function gets really close to as x approaches a is the limit. Okay, so that L is a y value. Okay, and so earlier, I think it was Umar who said this, and correct me if I'm wrong, but I believe he said something along the lines of when x equals this, y equals this. And so now instead of saying, okay, when x is exactly at this value, y is exactly this value, we are going back to this last part that Eric said right before break, which is we're zooming in on a small part of the graph and we're describing what happens there, okay? Now, there was also a slide in your Desmos activity that says the limit does not care what the value is actually there. It just cares about how close it gets to a specific value, okay? Now that right there is a very grown-up concept. It's a very mathematically mature concept. It's not easy to get right away, okay? But at the end of the day, what we're looking for is what y value does something get really close to, okay? So knowing that, let's go ahead and try this diagram. Okay, let's unpack it a little bit more than Desmos did for us. Okay, so here's a graph, okay? It's a weird looking graph. It's got some open circles, it's got some closed circles, it has some lines and some curves, okay? But let's take a look at question A. So this question, I would say, as the limit as x approaches 0 with a minus sign of f of x equals, okay? Now, let's think about this sentence frame that we have here. So as soon as we see limit, we know we're looking for the y value, right? The y value that the function gets really close to when x approaches what number, like what x value are we looking for in this particular problem? And you can go ahead and type that in the chat or you can unmute yourself, but what is the y, or what is the x value that we're looking for here? Exactly, we're looking for 0. So we want to see the y value that the function gets really close to when x approaches 0, okay? So if I zoom in, let's see if I can make the highlighter smaller. This 0 is this 0, okay? Now, if you look at my sentence frame, you'll notice that it says, when x approaches 0 from the left. Where did I get that from the left before from? Because we haven't seen that yet. Where did I get from the left? Yeah, that tiny, tiny little minus sign there. 0 with a superscript minus. That minus sign means I'm going to look at my picture and I'm going to see what happens when I get close to an x value of 0, but from the left-hand side. Okay? So let's go to our graph. If I'm tracing from the left-hand side, I'm going to start like somewhere over here. Okay? And I'm going to keep tracing the graph until, where is x equals 0? Like on my horizontal line, where is x equals 0? Maybe we should label that. Like on my horizontal line, I'm not asking for the y value. I'm asking for where on this horizontal line is x equal to 0. Yeah, it's x equals to 0 right here, right? X equals 0. Right? And then this one, it says 2, but it's really x equals 2. Okay, so we're looking for approaching 0, but from the left. So I'm coming this way, I'm coming this way. What y value does it get close to? It gets close to 1. Okay, does it get to 1? Okay. The y value that the function gets really close to when x approaches 0 from the left is 1. I don't care that it doesn't get there. I only care that it gets really close to that value. Okay. So this one is like the L that we saw up here. That is our limit or our y value. Okay. So the y value that it's getting really close to is 1. So that means that the limit as x approaches 0 from the left is 1. Okay. All right. So let's unpack part B. What makes part B different than part A? Okay, that plus sign, right? Everything else is the same. So let's zoom in a little bit. We are saying the limit as x approaches 0, right? Approaches 0. Now this time though, that little minus sign is not a minus sign, but that little sign is a plus sign. That plus sign means that we're looking at the graph, but this time we're coming from the right-hand side. Okay. So if we go to our graph and we trace, coming from the left, from the right, I trace. What y value is that graph getting really close to from the right? 3. Okay. So that means that our limit as x approaches 0 from the right is 3. Okay. So when we looked at this picture, we found where the x value was that we were interested in. And then the little minus sign meant we were looking from the left. The little plus sign meant we were looking from the right. And we got numbers. We got the limit from the left-hand side is 1, and the limit from the right-hand side is 3. Now, what do you think that part C means? Both together. How do I know that from the equation? There's no plus or minus. Okay, so if there's no plus or minus, right? Like in A, there was a little minus sign. In B, there was a little plus sign. In C, there's no superscript with a plus or a minus. If there's nothing written there, that means we want to see from both sides, okay? So the y value that the function gets really close to when x approaches 0, and we know it's 0 because we have this little 0 here, from both sides. Okay. What do we think our answer is here? Okay, I see a D and E. I see a 3 and 1, or we find the average and go with a 2, 1 and 3. Okay. So we saw something like this in one of the Desmos screens, right? There was one slide, I want to say it was like 2E or something, or 2C, where it asked you what the limit was, and then the picture kind of looked like this, where from one side it gave you one value, but from the other side it gave you a different value. So here's how we handle these mathematically. If we have a picture of a graph where on one side we're getting one y value, but on the other side we totally get a different y value, if those values are not the same, right? So if the left value and the right value is not the same, then we say that limit does not exist. That's what that line from Mean Girls means. That if we're looking at a picture where both sides don't match up, right? They don't agree, that one side gets to a y value of 1, the other one gets close to 3, they're not the same, then we say the overall limit does not exist. Okay? And so that was actually one of the questions that folks had from earlier, is like, what does it mean when it says a limit does not exist, or what does it look like? Okay. And so we'll put some more fancy words with what this means and like what we call this kind of picture, okay? But in this case, because the left and the right-hand limit are not the same, we can say the overall limit does not exist. Okay. Now, before we answer part D, I'm going to scroll up to our intro picture. Okay, we had this picture in the beginning. Can someone give me an X value? Don't type it in yet. Can someone give me an X value where the overall limit does not exist? Okay, so think about that for a moment. What is the picture going to look like if the overall limit does not exist? And go ahead and type in your answer in 3, 2, 1. Ooh, Isaac with the formal notation, x equals -1. I love it, I love it. So the x value where it does not have an overall limit is x equals -1. Because what's the left-hand limit? What y value does the function get close to from the left-hand side of -1? It gets to -2. Exactly. What does the function have as a limit from the right-hand side? -1. Exactly, folks, exactly. So this x value right here, okay, that x value does not have an overall limit, but it does have a left-hand limit and a right-hand limit, okay? All right, let's finish up one last part for example 1, which is f of 0, okay? So f of 0 is what we started out with. We know that means the y value of the function, right? So f of 0 means if x is 0, what is the y value? Okay, in other words, the y value of the function when x is exactly at 0 is, da, 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 what is that y value? 3. Yes, it is. Now, how do we know that it's 3 and not 1? But a point of discontinuity could be 1 as well. Like, what in our picture means that the y value is 3? Yeah, exactly. The closed dot. Like this dot right here, and I feel like I'm like going overboard with the colors, but this dot right here is filled in. That means that that is the y value at that x value. Okay, so at x equals, or at the 1, it's not filled in, so it's not going to equal 1. Okay. All right, let me zoom in for a moment so we can kind of look at that. Are there any questions about example 1 before we move on to example 2? All right, well, let's take a look at example 2 then. Okay, so how do we find limits? Now that I think was a question from earlier as well. How do we find limits? And whether you read down further into the notes or not, I really encourage you to just think about how you word your questions, right? So how do we find limits? Now it turns out there's a number of different ways. The first way we're going to do is from a graph, okay? So we can look at a picture and find limits. And we just did that, okay? But let's practice it again. Same picture, but what's different about these questions now? Everything looks really similar to me. What's different about this example and example 1? It's a 2, not a 0, okay? So Brian said it really well. X is approaching 2, okay? So I want you to take a minute. I want you to go ahead and try and answer these questions, okay, on your own. And we're going to go ahead and come back together and just check through the answers. Okay, so take a moment, see if you can take what we learned in example 1 and go ahead and answer these questions for example 2. How do we find limits from a graph? Okay. Right. So let's take a look at question A. All right. Now I've included these sentences here just because sometimes when we learn new notation, it's so hard to remember what the question's actually asking. Okay. Now, as we move forward, though, like by next week, I won't be having these sentences here anymore. So it's something that you want to really make sure that you understand as you read just the limit question, like what is it really asking you? Okay. So part A, the y value that the function gets really close to when x approaches 2 from the left is. Anybody have an answer for that? What y value is the function getting really close to when x goes to 2? Yay, it's getting close to 5. So my answer here would just be 5. And I'm saying I'm approaching 2 from the left is 5. Okay. All right, what happens when we approach x equals 2 from the right? What y value is that going to? I see a 5 again. Do we agree with that? Do we disagree? 55? Probably not. I'm pretty sure you meant 5. Okay. All right. So this answer is 5. Okay. Now, just to kind of use some colors to help us think about this, when I'm coming from the left, I'm tracing the graph this way. Right? So I'm seeing what happens as I come from the left-hand side of the x value I want. Now, sometimes, especially when we're sort of starting this, I find it helpful to mark out what x value I'm looking at. Okay, so some of you might find this helpful. Others of you are like, nah, I totally got it. And either way is fine. Okay, either way is fine. But the trick is you have to find a method that works for you. Okay, the worst thing that you can do for yourself right now is be like, I have no idea what she's saying, so I'm just going to guess numbers. Okay, that is a really bad place to be. It's a really bad decision to be. It's not that being confused is bad. It's that when you're saying, I'm just going to guess some numbers, we got to figure out how these numbers come to be. Okay, so now when we're looking from the right hand side, that was part B, we're tracing from the right and we're getting close to that x value. Okay, so that's how people are getting 5. Now, what would we say is the overall limit when I'm approaching 2 from both sides? Yeah, exactly. Both sides are getting to 5. So because they agree, we can say that the overall limit is 5. Okay.
For A, when it says so we're coming from the left, how do we know we start like from there and not all the way, like the bottom on the left?
That is a great question. So earlier, Eric said something that we're sort of zooming in on the picture and looking at a very small part. I would use that language to help you think, like if I'm zooming into this picture, getting as close to x equals 2 as possible, the other part doesn't really matter. So I want to pick points that are really as close to my x value as possible.
Okay.
Okay.
Thank you.
That's a great question. Thank you for asking that. Okay. So we've got one last part here, which is f of 2, right? So the y value when the function when x is exactly at 2. What do we think here? There's an open circle here, right? Now, we have to check though, along that blue dotted line, are there any other points on that line? Like, did I have, like in the other graph, maybe like a pink point somewhere else? No, we didn't, right? There's no other defined thing for it. So the y value of this point is undefined. Okay, the y value of this point is undefined. Now, before we leave the graphing, let's go back to that graph we saw at the very beginning of class. Okay. And we had mentioned earlier that there was no overall limit at x equals -1. Okay, everyone was spot on that. Is there an x value here that has a limit, but the y value is undefined? Okay, it has a limit, but the y value is undefined. Okay, so I see a couple different answers. X equals 3. All right, let's take a look at that one. What do we think? At x equals 3, there's a limit there, right? What's the limit at x equals 3? No, what's the limit as x equals 3? Okay, the limit as x approaches 3 of this function is 1. What is the y value at that function? So what is f of 3? It's 2, okay? So the limit exists, but the function is also defined there. So now let's check out that other x value that folks were looking at, which is -3.5, which looks as if be about here, okay? What is the limit as x approaches -3.5? Right, it looks about 1/2. Sure, I'll go with that, okay? What is the y value at -3.5? It is undefined because there's no other dot there, okay? So f of -3.5 equals undefined, okay? So what's kind of cool is calculus gives us a way to describe these graphs that are not just your everyday graphs. So these graphs have holes, they have points of discontinuity, they have all sorts of things happening. And now we can describe in more detail what's happening at different points in the graph, okay? Okay. So one important takeaway for today is I want us to feel confident finding limits graphically. Okay, so when we see a picture, how do we find left-hand limits, right-hand limits, overall limits, and then not forgetting things that we knew when we walked in the door is what the y value is at a given point, okay? Now, in these last 8 minutes or so, I would like to get started on how we can find limits if we don't have a picture, okay? Now, if we don't have a picture, then we call this finding limits algebraically, meaning that we're going to not have a picture and see what we can do. Now, we can always check our answers by graphing the function, okay? We can always do that. But let's see what we can do without that piece first, all right? So let's take a look at example 3 here. We've got the limit as x approaches 5 of 2x squared minus 3x plus 4, okay? What shape is this graph? First of all, what is our function that we're looking at here?
A parabola?
It is a parabola, okay. Facing up or facing down? Yeah,
Opens upward.
it's facing upwards, right? So 2x squared, we know the x squared is positive, so that parabola is going to be opening up, okay? Now, what this question is saying is what happens, like what y value does this graph get really close to when we plug 5 in for x when we get really close to x, okay? Now we know that this is a parabola. Does the parabola have any weird things like points missing or like other weird things that we saw in some of the other pictures? No, right? It's like a pretty straightforward graph. So when we know that the picture is like a pretty straightforward graph, then one method we should always start with is called substitution. And all that means is you're going to take the x value they want you to get really close to, and you're going to plug it into your function. Okay? No matter how complicated the function looks, you should always start with substitution. Okay? So I'm going to say 2. I'm going to plug in 5 for x. So 5 squared minus 3 times 5 plus 4. Okay? And let's do a little mental math here. We have 2 times 25 minus 15 plus 4. And we should get 50 minus 15 is 35 plus 4 is 39. Okay? So even though I took away the pictures, what does that 39 represent? Okay. This 39 represents the y value as x approaches 5. Okay. Yeah, 39 is a y value. Okay. So just so I don't keep going back and forth between screens, let's do example 4 and then we'll go to Desmos and then we'll wrap things up, okay? So no matter how gross the function looks, like I don't really know what x cubed plus 2x squared minus 1 over 5 minus 3x looks like. But one thing we should always try first is substitution, okay? So everywhere we see an x, we're going to substitute in -2, okay? Does everyone see that negative in front of that 2? All right. I know it's kind of small there. It's like connected to the arrow, but when we're reading these, we really want to make sure we read the question accurately, okay? So let's plug in -2 and see what happens. -2 cubed plus 2 times -2 squared minus 1 over 5 minus 3 times -2. Okay, so all I've done is plug things in. Now, we really want to make sure that we are accurate with our computation, okay? So -2, when I cube that, is that going to give me a +8 or a -8? It's going to give us a -8, okay? And we want to make sure we know that it's an 8, not like a 6, right? It's not 6 because it's not 2 times 3, it's 2 to the power of 3, okay? All right, what about the next term? 2 times -2 squared. What value is that going to give us? A +8, good, so +8, and then -1 over 5, plus or minus here? +5 plus 6, all right. And so we clean this up and we get -1 over 11. Okay, so it's not a whole number, it's not 39, but that's okay. All right, what does this answer represent? It is the y value as x approaches -2. Exactly, exactly. Okay. All right, so let's keep those numbers in mind, 39 and -11, okay? I'm gonna stop sharing my screen. Ah. All right, so one of the things that you can use Desmos for, of course, is you can graph things, right? And so I'm just going to type in y equals, whoops, y equals 2x squared minus 3x plus 4. So that was example 3, right? And now we said that when the x approaches 5, that our y value got close to 39. So the cool thing about Desmos is I can sort of like move it around and see, okay? And so let's see, this is at an x value of 3.5. So we got to keep going. Whoop. Right. So 5, right? So when the x approaches 5, the y value is 39, okay? So that's one way that you can check your answer when you're working through these kinds of questions. All right, let's try the other graph, weirder looking graph. Y equals x cubed plus 2x squared minus 1 divided by 5 minus 3x. Okay, so let me hide that first picture. Let's focus on the blue curve. Now we wanted to see as x approaches -2. So let's see. Okay, there it is, -2. And I bet if you type in -1/11, you will get that as the value, okay? So let's see, -1/11. Yeah, -0.090909, and that is a rounded version, but that's what it gets to, yeah. Okay. So we're starting to look at equations without the pictures, but I still wanted to keep that in mind, that as we are looking at these equations, what in the world do all those numbers mean? It's not just how fast you can do the numbers or how fast you can crank through the problem or factor or whatever other skills we might learn, but I still want us to keep in mind what we're looking for. What does that number actually mean at the end of the day? Okay. So we are going to stop here for today. But before we leave and depart to whatever we are doing next in our day, I just wanted to bring up 2 options that Isam has for his tutoring sessions. So I was going to put together a Google form and totally didn't happen. But we'll just go ahead and type this into the chat. So Isam, please correct me if I'm wrong. I believe that you said that one option is that you would work with students right after class on Wednesday.
Mm-hmm.
How do we do a Zoom poll? Is that a thing? How do I not know these things?
Oh.
All right, Wednesday after class, and that would be for how long?
Let's see, Wednesday. We could do 2 to 1. Or we could do, or sorry, 12 to 1 right after class.
Okay. So option 1 is Wednesday after class 12 to 1. Option 2 is Thursday 9 to 11. 9 a.m. to 11 a.m. Okay.
But what we're trying to find out is primarily if people prefer to stick around after class immediately or come back on a day where there isn't a class like Thursday. And yeah, these times are definitely flexible because I understand there are people that have class after and whatnot.
So
and then we can also,
oh, go ahead.
What was it? I was saying we could also work around having classes or like having sessions like pop out of nowhere. So like if some people can afford getting there on a particular Friday or Saturday and have the availability to do it, we can always do that too. But I have to turn in like a fixed schedule for Mesa so that they can like schedule me consistently. But we can definitely do some more that are outside of that schedule.
Okay, I see Thursday. Okay. What is your availability on afternoons? Because I know you have other.
Yeah.